Okay, it's thinking. Again, let's try it now. All right, the next section is what happens when we transform it. Take a look at the recipe. Here was our base. Here's the value of x. And so this is our horizontal transformation. We see a k. Here's our vertical transformation. And we see an a being multiplied to the base. That's our reflection and dilation information. So it's exactly the same as all the other transformations on parent functions that we've handled previously. And they all do the exact same thing. And I'm going to try to get this whole shifting thing. Hi. So many giggles. Yeah. Okay. So H is the horizontal shift. A positive H value shifts it to the right. A negative H value shifts it to the left. But notice when you plug it into that recipe, a positive H value will make your equation have a minus sign in there. And a negative H value shifting to the left will make your equation have a plus value. It's confusing. Be careful. K is our vertical shift, and this one's not confusing at all. A positive K shifts it up, a negative K shifts it down. A, handling your reflection when it's negative, the function is reflected across the x-axis. Ignoring any positive or negative symbol on A. If it's greater than 1, we have a vertical stretch. And if it's smaller than 1, we have a vertical compress. Thank you for the heart. Feels very familiar at this point, yes? I'm a broken record with these transformations. All right, which of these do you want to see as the example? 1, 2, 3, or 4? 4. All right, so looking at 4, let's identify the things that we have. This is the base because it's the thing that has the exponent. Looking at the exponent, we're adding, subtracting things. So we have a horizontal shift. Looking right after the base and the exponent, I see that we're adding, subtracting. So we have a vertical shift. And then looking in front of the base, I'm multiplying by some number. So we have a reflection or a vertical stretch or a vertical compress. All right, let's start reading these. The first thing that we look at is our green thing. All right, so this is A. A is 1/2. Is A positive or negative? It's positive. So if it's positive, do we have a reflection? No. All right. Is 1/2 greater than 1 or smaller than 1? It's smaller than 1, which means we have a stretch or compress. What was it? Compression. All right. So I'm ready to write my first statement. There is a vertical compression of scale factor, whatever the value of A was. That's the information that A gave me. In the exponent, that's H. What's the value of H? -4 or +4? Remember that your recipe for these transformations looks like this. So you're going to compare the signs right here. Yeah, when the signs are the same, it's a positive. So H is a +4. So is it moving left or right? To the right. So that's our next thing. We have a horizontal shift of 4 units. And this is the information that I'm getting off of the thing I highlighted red. Off of H. And lastly, we look at K. What's the value of K? What's the value of K? -2. Again, in order to help you figure it out, you got to look at the sign here in our recipe and then compare it to the sign in the equation we're looking at. If they're the same, yeah, if they're the same, it's positive. If they're different, it's negative. All right, which means we have a vertical shift. How many units? 2. What direction? Yeah, it's a downshift. I forgot to write it on the horizontal one. Sorry. Questions, comments, concerns on the transformations? Is okay? All right. You have plenty to practice. You've got 3 others. And now we can graph. We're going to graph using the transformation rules. Okay? So we want to start off by graphing the parent function. Okay? I'm going to graph the entire parent function in orange so that way we can see it easily. Okay, parent function, we have to think about the base. The base is 2. So our parent function has an asymptote here on the x-axis. Parent function, when the base is 2, goes through, has a y-intercept at 1. And then 2 to the first power, 2 to the second power, 2 to the third power, 4, 5, 6, 7, 8. And then here it's headed toward 0. All right, so there's my parent function. So this is f of x equals 2 to the x power. Because that's my parent function, because the base is 2. Reading the equation, what transformation is happening to this graph? Say that one more time. 5 units left. All right. So I'm going to grab every point on this thing and I'm going to shove it to the left 5 units. Am I moving the asymptote? No, it doesn't appear to be moving. So I'm going to darken in that asymptote. I'm using purple now just so that we can see it a little bit better. All right. And all these outs are going to move to the left 5 units. 1, 2, 3, 4, 5. This one ends up here. This one ends up here. This one is 1, 2, 3, 4, 5 ends up here. This one is 1, 2, 3, 4, 5 ends up here. And then this one is 1, 2, 3, 4, 5 ends up here. And so what I graphed in the blue and purple is the transformed function. It's read this way. F of x equals 2 to the x plus 5 power. Did you hear the pauses? Did you hear where I rushed? I'll say it again. F of x equals 2 to the x plus 5 power. Where I'm rushing, it's all pushed together. Say that again. We need to go like that a bit more. Okay. The parent function is pronounced f of x equals 2 to the x power. Please feel free to write that in English for yourself, especially if the math notation makes you go, what the function? I know you can do the characteristics at this point, so I'm going to leave that for you. Any questions on how we would graph using transformations? Because this application is a transformation, I really want to see you graph the parent function and graph the transformed function. Use a highlighter to let me know which one is which. And label your functions the way you see that I've labeled them here, where one is labeled as the parent and one is labeled as the function we were provided. Comments, questions, concerns? All right, looks like you've got another full page of these. I am very happy with you being able to graph them, even if it's a decay, like in number 8. So if it's all right with you, we're at 3:15 and we're trying to catch up. I would love to talk to you about how you solve exponential functions, because this one gets weird. We're back to the weird world of all the algebra notation doing funky things. Okay, let's start on this. That way we can devote some class time next time to getting into some more examples. All right, lesson 3, solving. This is method 1, same base. This is the same base method. What we're going to do is step 1, we're going to use the properties of exponents in order to simplify both sides of the equation and rewrite it so that way both sides have the same base. If they already have the same base, then steps 1 and 2 are done. If they don't, we have to do a little bit of work. Once we get both sides of the equation in the same base, you can just work with the exponents and ignore the base. Okay? We've got 1, 2, 3, and 4. I'd like to start with 1 or 2 first. Which one would you like to see? 1 or 2? 2. Okay, step number 1, simplify. Any simplification that needs to happen? Not yet. There's no simplifying. We don't have bases multiplied together. That's what we're looking for. Step 2, we make sure that each side of the equation is written with only one base and that those bases are the same. Do we only have one base on the left side? Yes, that base is 5. Do we only have one base on the right side? Yes, that base is 5. The bases are the same. Since the bases are the same, you can essentially ignore the bases and rewrite this equation as just the exponents. And that's the equation to solve for n. This one I know everyone can solve. Very Algebra 1. Things get weird when you look at, say, question number 4. Oh, dear God. Okay. First off, let's identify our bases. There's a base because it has an exponent. This is a base because it has an exponent. This is a base because it has an exponent. And this is a base because it has an exponent. Are they all the same? Yeah, we have all the same bases. Okay, that's going to be super helpful for step number 2. Let's simplify each side of the equation. When I look at just the left side, I have 10 to the negative 4 times 10 to the 9. What do I do to get that to be one base? You add the exponents. Whenever you're multiplying things with the same base, you can add the exponents. So the left-hand side is going to look like this. I'm going to do the exact same thing for the right-hand side. And I'll get some color going on this in just a second so that it's easy to see what I've put together, okay? Give me a second. Let me get some color going. Okay? Thumbs up? Or a nod. A nod works too. And now we're back to the same question from number 2. I only have one base on each side of the equal sign. Are the bases the same? Yes, which means I can essentially ignore the bases. I'm not canceling the bases, okay? I'm ignoring the bases. And I can work with just the exponents. Yes, I simplified negative 4 plus 9 into 5. You can solve that equation. That's an Algebra 1 looking equation, yes? The hard part is mucking with the exponents. Oh, and I got a thumbs up in the chat. Thank you for the thumbs up in the chat. That works too. Now the problem comes in when you have equations that don't have the same base. Take a look at questions 5, 6, 7, and 8. None of these have the same base. So we got to put a little more work into it. Which one do you want to see me play with? Number 9. All right. They don't have the same base. Can I convert any one of them into something that would have the same base as the other? Like, is 27 3 to some power? Yeah. Yes. Okay. What is 27? 3 to the power of 3? Okay. So that's this piece right here. And then we're raising this to this power right here. So 3 to the 3 is 27. And so 3 to the 3 is being raised to the power of 2x plus 6. I didn't do anything to the right-hand side. Now we're going to simplify that left side of the equation a little bit more. Do you remember what you do with a power to a power? Try again. Multiply. You multiply the powers. So the left side is going to become 3 to the power of 3 times 2x plus 6, that entire group, 2x plus 6. Are the bases the same? Yes. And so now I can essentially throw them away, and this becomes the equation that I am solving. And once again, we're back to a happy, fun Algebra 1 type equation that hopefully by now everyone feels really comfortable solving. If you don't, it's fine. I'm staying after school today. Text mom, dad, if you want to stay. I'm looking to stay again tomorrow, Thursday, and I'll be here for sure Saturday morning from 9 to 12 for 3 hours. Let me know if you're staying so that I can tell the principal and we can order you pizza. Pizza emojis in the chat if you're showing up. Questions on how you mess with the bases to force them to be the same? I think I want to stop here. Say that again.
Actually, no, never mind. I just thought it made sense.
Okay. I think I want to stop here for now to give you guys a chance to work on the graphing and to start on this. Okay? So you've got about 30-ish, 35 minutes left in class to get started on it. And next week, we'll continue. Thank you very much for joining in on the live. You ready for me to grade stuff? All right.
Started at 8.
Yeah.